Okay, so let's dive into something that sounds, well, kind of impossible, right? We're talking about AI models that are infinitely deep, but, and this is the crazy part, they can be trained using the memory of just one single layer. This isn't just a small tweak, it's a completely different way of thinking about how we build these massive neural networks.
But before we can really appreciate the solution, we got to talk about the problem. What's the biggest thing holding us back from building even bigger AI models? It's this one major bottleneck. And believe me, it affects every single large model you hear about today.
And that bottleneck? In one word, it's memory. Yep, it's not just about getting faster chips or throwing more data at the problem. The real limiting factor is the sheer amount of space a model needs just to be able to learn. This is the wall, the big one, that we keep slamming into when we try to scale things up.
So, you might be asking why. Why does it need so much memory? Well, it all comes down to how these things learn, a process called backpropagation. To put it simply, for a model to learn from its mistakes, it has to kind of retrace its steps. It has to look backward through every single layer it just went through. And to do that, it has to remember everything it calculated along the way, every output, every activation from every layer.
And that brings us right back to this wild idea, this paradox. If every new layer costs you more memory, how in the world can you have an infinite number of them but only pay the memory price of one? It totally sounds like it breaks the rules of the game, right? But stick with me, because that's exactly what we're going to unpack.
All right, so let's really dig into this problem. We'll call it the deep learning memory wall. And it's a perfect name because it really is this massive barrier that researchers are desperately trying to figure out how to climb over or, just smash right through.
Think of training a normal deep network like a little dance. First, you have the forward pass. That's where the data moves forward step by step through all the layers. But then comes the catch. To do the backward pass, which is where the actual learning happens, the model has to remember every single move from the forward dance. It has to store every intermediate result. And that's the key takeaway. To learn by going backward, you have to remember everything that happened going forward.
And this chart here just lays it all out perfectly. Look at that relationship. It's a straight line. The more layers you add, let's call that L, the more memory you need. It scales 1 to 1. In computer science terms, we call that OL complexity. And that, my friends, is why it's such a huge, massive bottleneck when you start talking about models with thousands or even millions of layers.
Okay, so we've established the problem. The memory wall is real. How on earth do we get around it? Well, the answer, the big breakthrough, came from a super surprising discovery about what's actually happening deep inside these networks.
So some researchers were playing around with these really deep networks, specifically ones where many of the layers share the exact same settings. That's a technique called weight tying. And they noticed something weird. After the data passed through a certain number of these repeating layers, the output just kind of stopped changing. It would get refined a little bit, then a little less, then even less, until it just settled into this stable final state. They called this an equilibrium.
And that insight sparked a revolutionary question, a real light bulb moment. If all these extra layers are just nudging the answer closer and closer to that one final stable point, why are we doing all that work? What if we could just calculate the final answer directly? Just jump straight to the end without taking all those tiny little intermediate steps? Why bother?
And that one question, that's the core idea behind a whole new way of thinking about AI models. Models that don't build an answer layer by layer, they solve for it. And that brings us to the star of our show, the Deep Equilibrium Model, or DEQ for short. So get this, instead of a huge stack of layers, a DEQ has just one processing block. But it also has a solver. And the solver's entire job is to keep feeding the output of that block back into its own input, over and over, until it finds that fixed point, that moment where the output basically stops changing. That's the equilibrium.
Yeah, this comparison really nails it. On the left, you've got the old way, stacking layer on top of layer on top of layer. It's sequential. On the right, you have the DEQ. It's using this clever mathematical solver, basically a root-finding algorithm, to just find that final stable answer directly. It's a huge shift in thinking, right? From step-by-step construction to direct calculation.
Okay. But wait a minute. This raises a massive question. If learning means going backwards through the layers, and we don't have a stack of layers anymore, how does the model learn at all? How can backpropagation possibly work here? Yep, that is the million-dollar question. Normal backpropagation needs that chain of layers to work its magic.
But here, our infinite network is basically hidden inside this black box solver. It really does seem impossible. But there's a kind of mathematical superpower that saves the day.
And that superpower has a name: implicit differentiation. It's this really elegant trick from calculus, and what it lets you do is figure out the gradient, the thing you need for learning, by only looking at the final answer, that equilibrium point. You don't need to know how the solver got there. You don't need to see its work. You just look at the final state, and poof, you can calculate what you need to learn.
And this quote from the original paper just says it all. Constant memory. That's the holy grail. We've gone from O of L, where memory grows with layers, to O of 1, where it's flat. It doesn't matter how deep your model feels or how many iterations the solver takes, the memory footprint for training is always the same. It's just the memory of that one single block. The memory wall, it's not just climbed over. It's like it's not even there anymore.
So let's just break it down one more time. It's a simple two-step. Step 1, the forward pass. The solver finds that final equilibrium point Z star. Step 2, the backward pass. We use that magic implicit differentiation trick to calculate the gradients directly from Z star. That's it. No need to store a massive history of every little step. It's completely bypassed.
Now, as cool as this implicit differentiation trick is, it's not the only game in town. It's actually one point on a whole spectrum of different methods, and each one has its own pros and cons, trade-offs between how hard they are to code and how efficient they are.
And this table gives you a great overview of that landscape. So on one side, you've got the standard way, just unrolling the process. It's easy, it's built into most frameworks, but man, is it slow and a total memory hog. On the total opposite end, you've got our hero, implicit differentiation, super efficient, constant memory. But you got to write custom code, which can be a pain. But then, look at the middle. There are these cool approximations like one-step differentiation that give you the best of both worlds. Almost as fast and light as the full implicit method, but way easier to actually implement.
So, okay, we've gone through the how, but what about the so what? Why does any of this actually matter in the real world? Well, to put it lightly, this is a potential game changer for pretty much everything in AI development.
And I'm not talking about a tiny incremental improvement here. Look at this number, 88%. In some tests, DEQs have shown an 88% reduction in memory compared to other top-tier models doing the same job. That's not a step forward, that's a giant leap.
And here's the best part. You're not trading performance to get that efficiency. Nope. DEQs have been shown to get results that are just as good, and sometimes even better than, powerhouse models like Transformer XL. And they do it with a tiny fraction of the memory. Just think about what that means. It means we could train much bigger and more powerful models using the same hardware we have sitting around today.
So this whole thing really leaves us with a huge mind-bending question to chew on. For so long, we've thought of depth in a network as something physical, something we have to build, layer by painstaking layer. But what DQs show us is that depth can just be a property of a system, something implicit that we can solve for directly. And that just makes you wonder, right? What else in AI are we building with brute force right now that, with just one clever insight, we could be solving for instead?